Hello, we will be solving a problem, this one, which is trying to match the expressions on the left to the time domain plots on the right. We would like to do it with few or almost no calculations. The problem is taken from the set transform chapter of the Linear Systems and Signals textbook by Lati and Green. Let's start with the first expression for x of z that we will express as the product of these two functions. Yes, I know that's x of z in Canada, x of z in some other places. The first and second term of this product are both associated with the same discrete exponential, and this product in the z domain involves a convolution in the time domain. You can pause the video at this point and look at those plots and see which one is x of n, that is the inverse of x of z. Let's say that at this point you narrow down the possible solutions to be the ones corresponding to plot 1 and 13. And the selection of those two plots come from what we are expecting to see when we convolve those two functions. At n equals to 0, x of n is equal to 1, and that is on plot 13, not on plot 1. So we can eliminate plot 1, and we can associate the expression on A with plot 13. From the convolution, we can also see the decay of x of n as n increases. For the expression in part B, we will focus on the poles and see that they are located within the unit circle and are complex conjugated. That corresponds to a decaying sinusoid, and leave us to the options of plots 8 and 9. As a sample at time n equals to 0 help us to discern between the two plots in the previous problem, let's pause and talk about how can we calculate that x of 0 in time relatively fast. Starting from the definition of the Z transform, we're going to evaluate the summation at n equals to 0 and realize that for n equals to 1 to infinity, that term goes to 0 when z goes to infinity. This is known as the initial value theorem. In order to estimate it, we're going to multiply and divide x of z by 1 over z squared. And realize that when z equals to infinity, those terms go to 0, and we end up with a final result of 1. And that's exactly what we're looking for. And we can see that plot 9 is the one that has that value, and the other one starts at 0. So we can eliminate that one. You can actually solve problem A using this initial value theorem too. For part C, we will simply evaluate that summation from k equals to 0 to 4, and simply calculate the inverse of those 5 terms yielding this expression. From here we can see that the only possible solution is the one in plot 18. For part D, we can simply see that we have a unit step delayed by 5. For part E, we will take the long division and calculate few samples of x of n. Problem F looks very similar to the first problem we did on part A. It is simply part A time shifted to the right by 1 and scaled by 0.75. And yes, the vertical scaling of all the plots is not the same. That's why the plot on 1 doesn't look like an attenuation of plot 13. For part G, we will once again concentrate on the poles by calculating the roots of the polynomial on the bottom and realize that they lie on the unit circle, complex conjugated. So that's a sinusoid. In order to discern between the two candidate plots, we will be using the initial value theorem again. By evaluating at z equals to infinity, we can see that x of 0 is equal to 1, that is plot number 4. For part H, we can see that we have two repeated poles at 1, and this corresponds to a ramp. Two possible candidates then are on plots 6 and 12. In order to figure out the final solution, let's take a look at the zeros. Let's start by multiplying the polynomial by z to the power of 6. Possible roots are factors of the constant term 4 over factors of the leading coefficient 1. Testing for z equals to 1, we can see that that is one of the roots. Let's find another root by taking long division. we can see that z equals to 1 is another root. So we have two zeros at 1 that will cancel the two poles that are located exactly at 1, 2. This will lead us to an expression for x of z, which is a polynomial of order 3, meaning that x of n is finite. For the last problem, we can once again use the poles, do long division, extract a couple of terms, and realize that this is a discrete exponential that is increasing its amplitude on time. We can also identify this with a table, Z-transform table, and identify that same expression 1.1 to the n u of n, which leads us to plot 16. Here is the final solution.